this one that I gave above, and then three others that I'm going to discuss separately. First, we can work from the DGA point of view using the algebra of sections over the nerve with values on E. And it turns out that defining a representation is the same as to give a degree 1 differential on this algebra. This point of view is very useful, but I'm not going to follow much on this direction. The other one that is more central to this talk is a fibration viewpoint. From this point of view, you can always think of a fibration as a family parameterized by the base. The fibers are the members of the family, and it is parameterized by the base. When what you put in the base is a group or a groupoid, you should think of it as a parameterized family with certain symmetries. And it turns out that you can always construct a Lie groupoid over your base that is usually called in the literature translation groupoid. No? It projects over the base, and it is a vector bundle over the objects of the translation groupoid are a vector bundle over the objects of the base. The arrows of the translation groupoid are a vector bundle over the arrows of the base. All these vector bundles are going to have the same dimension. All the structure map, source, target, multiplication, and unit are going to be linear, fiber-wise isomorphism. And to have one of these structures, which are called VB groupoids, vector bundles over groupoids, where all the ranks are the same, is the same as to give a representation. And there is also a nice point of view in which you can think of a representation as a groupoid morphism into the general linear groupoid. This general linear groupoid arises out of the vector bundle, and it consists of the fibers of the vector bundle as objects and linear isomorphism between two fibers as arrows. So ABC, no? Each of these point of view is very productive. Point A is, for instance, very useful to talk about cohomology. Point B, well, we will see later, no? But it gives you this translation groupoid. Point C allows you to talk about also characteristic classes, because you can pull back, no, cohomology classes on this more standard object GLE to G. So, but the problem with representations is that they are scarce. There are too little representations. There is no Jones representation. There is no Tanaka duality. And one heuristic explanation of this is that the vector bundles are too little so as to allow meaningful representations of Lie groupoids. No? You need more space. And this way, Camilo Arezabad and Marius Kreinig proposed representation up to homotopy as a generalization. This is just notation. I will, as usual, represent G, a simplex on the nerve, as a chain of composable arrows. And I will write as R, T, M minus R to the first and last part. So what is a representation up to homotopy? It's a representation of a Lie groupoid on a graded vector bundle. Okay? So it gives you a sequence of operators, Rn. They have to be compatible with identities and compositions and how. But let me explain a bit how this Rm acts. You pick a vector V that is over x0, is on certain En. Then you apply Rm, and it ends up at the over xm, but it shifted the degree. It ends up at a degree n plus m minus 1. No? There should be minus 1 here. It's a typo, sorry. And then, for instance, the degree R0 decreases the degree 1, R1 keeps the degree, R2 increases the degree 1. And so in low degrees, you can see that the R0 ends up to be a chain differential on the fibers. R1 is a chain map between the fibers, but these chain maps may not preserve the composition. Every time you have a commutative triangle on the groupoid, you may push forward with R1 of the first arrow, R1 of the second, or R1 of the composition, and they may differ, but they will be related by a chain homotopy given by R2. the same fashion, R3 is going to give some coherence between the homotopies and so on. So paradigmatic examples are that joint and quasi-joint representation of Lie groupoi that were not examples of representation, but of representations up to homotopy. And these particular examples are very important because they rule deformations and they appear in both spectral sequence that was developed also by Camilo and Marius. And it is interesting that they already, at that paper, the original reference, had to deal with tensor products of representation up to homotopy. And this is quite an issue. So this is the first approach to representation up to homotopy. But in the same fashion that we did for representations, there are others. So what are the others? As DGAs, the definition is very simple, and it's actually the original definition by Marius and Camilo, and they showed that they are equivalent. You start with a Lie groupoi, a graded vector bundle, pick this family of sections over the nerve of every member of every degree of the vector bundle, defining a suitable differential there compatible with the normalized cochains is going to be the same as representation up to homotopy. They show that both approaches are equivalent. And what about with the fibration approach? The two-term case, which corresponds to n equals 1 in the, remember that I use a vector bundle graded from 0 to n. So from 0 to 1 are two terms. This was done by Afonso Rezazas and Raj, where they showed that VB group was in one correspondence somehow with two-term representations up to homotopy. But this can be seen as an instance of Grothendieck correspondence between pseudo-functors and fiber categories. No, in his study of stacks, mainly, the original sources were using pseudo-functors, but at some point, Grothendieck decided, okay, to work with the equivalent formalism of fiber categories, but it is very important. The reason or the argument is that working with the fiber category is as if working without coordinates. And keeping track of all the cleavage, all the ways you are breaking this fiber category may be very expensive and problematic. How to do it in general is what I want to tell you today. No, this is our work with Giorgio. And then there is this third approach, or equivalent approach, that is looking at classifying maps into general linear groupoids. For n equals 1, two-term representations, we did that with David Stefani. And in general, is yet to be done. Even though I think it's very similar to what we did, just that there are smooth issues and this may be a bit annoying. But I want to focus on this, on how to represent the representations up to homotopy as fibrations. So what is our main theorem? Well, we say that something is a higher vector bundle if it is a simplicial vector bundle over the nerve, satisfying that is a simplicial fibration. And I will get into the definition of simplicial fibration later. Can be set theoretic simplicial fibration. It doesn't matter the smoothness. But so it's this. You have the Lie groupoi, you look at its nerve, and you look at the simplicial vector bundle over it. And our theorem says that if you start with a Lie groupoi and a graded vector bundle, there is a 1-1 correspondence between representations up to homotopy from G to E and higher vector bundles over G with core E, and admitting a cleavage that I will define later. I just wanted to tell you a bit of the taste of the theorem. What does it mean core? I will be very sloppy, but actually I will be very precise, but very short. You have a simplicial vector bundle over G, that is a groupoi. You can restrict it to the unit manifold, viewed as a simplicial, constant simplicial object, and you will get a simplicial vector bundle over a manifold. And by Dolkan, this corresponds to a chain complex, and this is going to be the core, if you want. And this normal coherent cleavage is the whole key of the situation. But this, as I was saying, is a coordinate-free approach to representation up to homotopy. And heuristically, you should think of this V as the homotopical limit of the pseudo-functor that goes from G into the graded vector bundles, vector spaces, graded vector spaces. So you see, forget about the smoothness and linearity for a moment. For each object, you have a graded vector space. And for each arrow, you have a map of chain complexes. No? Maybe here it should be said chain complexes. No? For each object, you have a chain complex. For each arrow, you have a map. For each commutative triangle, you have a homotopy, and so on. This is a generalized or weak functor. And the homotopical limit should be this construction that we have here. So our proof builds on previous work on simplicial manifolds by Kai Beren, Ezra, Andre Enriquez, Chen Chan. But there are these two simple ingredients also that I want to tell you later. New formulas for Dolkan, which I think are very surprising because Dolkan is very known and appears everywhere. And a theory of higher cleavages that allow us to do these push forwards between fibers of a simplicial manifold. And so to finish this part, let me tell you how our theory relates to the literature. First of all, it gives a global version. The infinitesimal counterpart is something that Rush worked out also, relating Weintrop's A modules with representation up to homotopy of Lie algeroids. A Weintrop's A module can be thought of as a Lie algeroid, no, over that is a vector bundle over Lie algeroid. Okay, it does not split giving a graded vector bundle, but using connections you can see, and actually Rush did that. You can see that they correspond. So this is the actual infinitesimal and arrow to our result. Then you can think of our result as a relative version of classic Dolkan, because if the base is just a point or a manifold, then you will get exactly Dolkan. Then you can think of it as a higher version of this Grothendieck correspondence that in the smooth linear setting was worked out by Afonso and Rush. And also, and maybe a bit surprising, but this can be a lax version, so a generalization somehow, of the work of Ike and Heutz, and that Lurie has in higher topo theory on what he called a higher Grothendieck correspondence. The point is that in the Lurie's higher Grothendieck correspondence, that was revisited later by Heutz and Moerdijk, they take the homotopical limit of a strict functor over there. This functor is taken to be strict. Okay. And this is, as you can see, quite limiting for our purpose. No? And so when you allow weak things, you get our result. So it can be seen as a generalization of that. What can be useful for? Well, to allow simple tensor products of representation up to homotopy, because now that we don't work with coordinates, we can do the level-wise tensor product of vector bundles. It's going to be a simplicial vector bundle. It's something that has to be worked out yet. No, I guess that it's going to be still a simplicial fibration, but at least this may simplify considerably the work of Camilo, Marius, and Benoit in tensor products of representation up to homotopy, which is quite difficult. But the philosophy here is again that of Grothendieck. Working with coordinates gets very dirty or difficult, but if you work coordinate free, things are simpler. We showed with using these constructions with Christian Ortiz and Fernando Susinski some homological version of Morita invariance of representation up to homotopy, but the total proof still is open. And it also gives a possible solution to a problem that Jim Stashev shared with us in the global Poisson seminar. No, here it is him. No, so he was telling us that it would be an interesting problem in its own right to define an inverse functor which makes use of a kind of associated bundle construction. So he was thinking, if you start with what Bloch and Smith called a local system, but it's a representation up to homotopy, how to build a global object over there? Well, we have a solution, just that things are a bit different. Here is an infinity groupoid, but you don't have smoothness, so it's just mutatis mutandis. I think you can adapt and possibly get a solution to that problem. So my time is almost Don't. But I will rush a bit about this part to tell you some of the basic ideas behind our work. So simplicial map is a fibration if it has the horn filling property with prescribed base. The idea is that for n equal 1, you want to lift a path, no? But you choose arbitrarily the point on the origin on the fiber. For n equals 2, you want to lift a triangle, no? But you prescribe two sides of the triangle. You determine a priori. And then, as I was saying, examples are if you have a local field submersion, you can take the smooth singular simplices. No? If you have groupoids, there is this notion of grothendieck fibration that is more general, no, for categories, but you can restrict it to groupoids. Then a map of groupoids is a fibration if only if the nerve induces a fibration between the nerves. So here is one of our definitions. And I must say that looking for higher grothendieck correspondences, Lurie and some other people decided to work with this Cartesian arrows approach somehow. There are some distinguished Cartesian arrows. And what we are saying here is different. It's saying, okay, a higher cleavage should have higher distinguished elements. The same as you have higher Cartesian arrows, you should have some sort of Cartesian triangles, etc. So what is a cleavage for us? It's a collection of simplices upstairs that gives you a unique feeling for any horn except the last one. It can be a bit weird, but it is this. Examples, I don't know, if you start with a locality of submersion and a complete Ehrman connection, well, you can lift, the cleavage would be a parallel horizontal lift of paths. This is the one cleavage. The two cleavages, you should say how to feel, and you can also do it by lift of paths, either horizontal or keeping track of the vertical direction, maybe with a metric or so. In a grothendieck fibration, this recovers completely the classical definition, because since things are one strict, there are no higher cleavages. No. In the classical theory of fibrations of groupoids, once you pick a cleavage, you gain a fiber pseudo-functor. To each object in the base, you give the fiber. To each arrow, using the cleavages as parallel transport, you can define functors between the fibers, and this is a pseudo-functor. No? So our higher cleavages allow us to develop a higher version of it. So once we fix a higher cleavage, we can define these push-forward operators. That here it is explained in detail, but I will tell you here for this design. You have a simplex with vertices 0, 1, I, n, and I want to do an elementary push forward of this simplex that sits, lives on the total simplicial object. I will pick this vertex and push it forward 1 unit. That means that this edge is going to be the horizontal lift using the cleavage of the corresponding edge on the base, on the projection. Once you have this edge, you can start feeling, using the cleavage, every simplex containing I and I prime, let's say. And at the end of the day, you gain an n plus 1 simplex like this, and then you can take the ith phase, so I erase this one, and I get an elementary push forward. These elementary push forwards allow me to take any simplex and push it forward to the last fiber. And I have to do it in a precise order and carefully, but I first push forward this object, now this one, and so on. So this is one of the things that we are going to use, the push forwards. Yeah. And the other is Dolcan correspondence. So every simplicial abelian group has its normalization. Dolcan tells that this is an equivalence. And what is the inverse for Dolcan? There is a simple conceptual nice way to express it as using the disjointness between the the normal and the Dolcan functor, let's say, no? Because the n simplices has to be those maps of chain complexes. But there are explicit formulas in the literature that, as far as I know, they don't have a geometric meaning. We propose, using the Horn filling approach, new formulas that I think they are very meaningful. So this idea is taking 0 as a distinguished vertex, and I decompose any simplex as a sequence of Horn fillings from 0. So here you see the triangle as a sequence of fillings from 0. And we have very similar formulas for injections. There is a classical duality between surjections from n to k and injection from k to n preserving 0, but this is not the difference. Here there is stronger difference. The idea is that once you keep track of the simplex by looking at all these informations or these Horn fillings, every time I perform a degeneracy or a phase other than 0 is combinatorics. You see here and here. It is a 0 phase that makes a lot of trouble because I have to rephrase everything. And some advantages of our formula is that they have a geometric meaning and they allow a generalization. So I think I have 1 minute only. So let me give you, starting with representation out to homotopy, we build very similar to our formula of Dolcan, but now it has pullback vector bundles. And I will tell you very quickly for the case of 2, how is this sum? The possible indices are 0, 0, 1, 0, 2, and 0, 1, 2. And the homogeneous elements correspond to the following. If I have 0, 1, 2, an element homogeneous of type 0 tells that there is non-trivial information over 0, but there is horizontal lift, and horizontal fill. For the EG10, there is a non-trivial information from 0 to 1 that this is a 0 section, no? That is over there. And then everything is 0. Again, it's flat. For the 0 to is similar, and the 0 to 1 has a trivial horn, but has a filling that is not flat, let's say, that has some curvature. And our formulas are a bit crazy. They are over there. I don't have time to explain them, but let me tell you that we show that this semi-direct product that we define with these phases and degeneracies is a higher vector bundle according to our definition. This recovers Dolcan and the Grothendieck construction. And for the other half, what we do is using the push forward to decompose any vector bundle using a cleavage as a direct sum. The problem is that the phases and degeneracies are not preserved in general. You need to add a condition for the cleavage. This coherence condition is a relation between the several cleavages at several degrees, and this is our theorem. The second half is that once you have a higher vector bundle and a normal coherent cleavage, then you get this is a semi-direct product of representation up to homotopy. So this completes the other way around, and thanks and sorry for the extra time.
Thank you so much. Time for questions. Ezra.
Actually, a very short comment.
Yeah.
So this is going back to Quillen's work on homotopy theory. He was comparing the homotopy theory of simplicial sets to homotopy theory of topological spaces.
Yeah.
And using the axiom of choice, he was able to prove a correspondence between those. But that increased interest in studying the homotopy theory of simplicial sets. And in the last few years, it was established that even without the axiom of choice, you can construct a homotopy theory of simplicial sets. And the notion of fibration in that setting, it's called the effective closed model category, is exactly with cleavages. So it's now increasingly becoming part of constructive mathematics and people interested in homotopy type theory and so on. So I just wanted to alert you to that close link to work that others are.
Thank you, Ezra. But do you know a reference on which this notion of one cleavage on each dimension is considered? Yeah, this? Okay.
Exactly. It's called an effective fibration.
I see. Okay,
Yeah.
okay. And it is the same thing that it has to be for every phase except for the last one? No, no,
No exception.
I see.
What?
Because for us, there is only one filling in the cleavage for every
Oh,
horn filling
Here's
except
an
for the last
interesting
one.
point. It's sufficient to define a Kahn vibration. You just need a left vibration
I see.
with target a Kahn. And so you never need to worry about it. There's a mistake in the literature. The definition of Kahn vibration is excessive. You don't need to worry about
I see.
the zeroth
I see.
horns at all, ever.
I see.
Yeah.
Thank you.
All right. Any other comments or questions? Raj, maybe.
Just two.
So one nice example of a representation of homotopy is when you have a cocycle and then you can form something that's like that cone complex that we saw in the previous
Yeah.
talk. Is there a simple description of what the V looks like in that case?
I haven't thought about it, but I agree that it would be very nice to give it a look. It is broken, but it's okay. No, I cannot pass. But it's okay. The slides. Don't worry. It's okay. I finished.
Time for one more quick question, if there is one. If not, let's thank Matias again.